Hello everyone, welcome to our discussion of section 2.3 where we will talk about composition of functions. Now last time in the last video we talked about combining functions, right? Combining functions was all about adding, subtracting, dividing, multiplying functions. But what about when we substitute one function within another function? Now you're used to substituting a number in a function, but what about substituting a function in another function? That is the main topic of this lesson, and it is called the composition of functions. Okay, that's when we replace one function inside another function. Now I want to remind you all that the best way to study and learn this subject is before you watch this video or attend the class, please skim through the section 2.3, no more than 45 minutes, 30 minutes depending on the length of the section, 30 minutes to 45 minutes would be optimum. Rarely, very rarely an hour is required as a skim through the section. Then watch the video and attend the class and take careful notes about any questions you might have or anything that you might hear or see that you think is important to you. And then, of course, review these notes and go over all the problems that are solved in the book in section 2.3, the solved problems, and solve those problems without looking at the solutions in the book. And return to this video and go over all the problems that I solve without looking at the solutions that I give during these videos. And then, of course, complete all the homework assignments by the due date. The homework is mandatory in this course, so this guarantees that you get due credit for it. And of course, review the older material, because the nature of this subject is that it's a cumulative subject. So we build on the stuff we've learned before. We use the skills and the methodologies we've learned before. Okay, before we actually get into deeper discussion of composition functions, one of the most important things about composition function is the notation used with composition functions. Now, just a minute ago, maybe 30 seconds ago, I mentioned that composition of functions refers to when we replace one function inside another function, right? There is a mathematical notation associated with that. Let's make sure that we understand first. So suppose we have two functions, let's say x minus 2 and g of x, and let's say this is x squared, right? We take two functions. Now, if we want to replace f of x inside g, then the notation for that is as follows. G, hollow circle, G composition of f in x. So people sometimes, they ask me, is this multiplication? No, this is not. We're not multiplying anything by each other here. This is just a name. It's a way we refer to composition of functions when the function f is replaced inside g. So in this notation, always the second function gets replaced in the first function. So what does this mean? It means that another way of saying the same thing is g f of x, like that. So I prefer this notation because it clearly shows which function is replaced inside which function. F is replaced inside g. The second function is replaced inside the first one. But in books and elsewhere in your online homework assignments and such, you will see both notations. So you should be familiar with both notations and what they represent. Okay? So, okay, now that we know the first function is replaced inside the second function, or f inside g, how do we carry this out? Well, wherever you have x in g, you must replace it with f. So in this case, f goes inside g, and x, so x minus 2 squared. Notice all of f replaced all of x, and then the power then applied to what used to be just x, but now it's x minus 2. And this is the composition of g of f in x. Sometimes you might see just this without the x. It's okay. This is the same thing as that. These two are equivalent. In other words, if you see this, it goes without saying that it represents this. Okay? So what about if we replace g inside f? How would that notation look? Okay, that's how this would look. So if g is going inside f, then f comes first, then the hollow circle, or the composition function notation, that's a hollow circle. That's not O, it's just a little circle like that. And then g in x. So now g is the function that comes second. So the second function always gets replaced inside the first function. Okay? So let's show, well, how about this? How would this notation be different? Well, now we have f, composition of g, like that. So this one clearly shows that g is going to have to be replaced in f. So these two are equivalent notations. Okay, now let's do what this notation is saying that we should do, which means place g inside f. Well, take a look at f. X appears only in this spot, right? We need to put all of g where the x appears. So x squared, instead of x minus 2, we have x squared minus 2, right? So g went inside f, like this. Okay? And this is the composition function. I'll probably repeat this again when we go to the worksheet in a minute. But when we do this, when we form composition functions, we're also often need to or interested in finding the domain of the resultant function. In other words, what is the domain of this? So we want to know, okay, now that we have the composition of g and f in x, what is the domain? Okay, and if we have the composition of f and g, with g going inside f, which is that, what is the domain of this resultant function? We're always interested in that, most usually. Okay, so the domain of the composition function, remember when we were talking about combination of functions, the domain of the combined function had to agree with both domains of the parent functions. Remember that? So let me repeat this. In the last video, when we talked about the combining of functions, the domain of the combined function had to agree and overlap with both domains of the parent functions. But when we form composition functions, it's if we're interested in the domain of the composition composed function or composite function, like these two domains should agree, not three. Two domains. Which domains are those? One, of course, the domain of the composite function itself should make sense for that function, but also this domain or the final domain of the composite function should also agree with the domain of the function that was replaced or embedded into the other function. So this domain, the domain of this composite function, should satisfy not only the composite function itself, which is obviously the case, but also that domain should satisfy the domain of the function that was embedded or replaced inside the other function. It should satisfy the domain of G, because it was G that was replaced in F. On this side, the domain of this function should satisfy itself, obviously, but also it should satisfy the domain of the function that was replaced inside another function, so F. Is this clear? So I want to make sure that you are clear about the difference between the domains of the combined function, which we talked about in the last video, and the domain of the composite function, which is the subject of this video. In the combined functions, the domain of the combined function must agree with both domains of the parent functions as well as the combined function itself. So all three functions, both parents and the resulting combined functions, their domains should overlap at some point, and they should agree with each other. In the composition of functions, the composite function will have a domain, right? That domain must satisfy the composite function itself as well as the function that was replaced inside another function. So this domain does not have to agree with the domain of G, but it has to agree with the domain of F, because it was the function F that was replaced inside G. On this side, this domain should obviously agree with the domain of this, whatever we have here, but also it should agree with the domain of G, because it was G that was replaced in F. It does not have to agree with the domain of F here, because it was G that was replaced in F. Okay? I hope this is clear now. If not, please rewind the video. This is very, very important. Okay, I wanted to first talk about the notation and talk about the domain, because we're going to use that extensively, and you should be clear how the notation works and how the domains are calculated, and the distinction, of course, between composite functions and combined functions. Okay? All right, so here we are. These are the notations that I just explained. Right, so composition of F on G, the G comes second, right? So it's the G that gets replaced in F, and as you can see, G was replaced in F. Okay, here we've reversed the roles, so now it's G composition F. Then that means the second function has to get replaced in G, so it's the F that gets replaced in G. So the resultant function will have a domain which should satisfy the function, the composite function itself, as well as F here, the domain of F. Here, the composite function has to have a domain that agrees with itself as well as the G, which was replaced. Okay? And of course, I might have had this because I copied this from the other worksheet. So the domain of a composite function, let me correct this. The domain of a composite function must be compatible with the domain of not its parent function. That's the combined function. Let me correct that, please. Must be compatible with the domain of the function that was embedded in the other function. Embedded means replaced in the other function. Okay, not both parent, that's combined. So I need to correct that on my worksheet, on my original worksheet, so it doesn't print like this. Okay, the domain of a composite function must be compatible with the domain of the function that was embedded in the other function. So it means the domain of the composite function must be compatible with the one that was embedded. Embedded means that one. Okay? Not with the domain of G, but with the domain of F. Not with the domain of F up here, but with the domain of G. Okay, and we'll do examples so it'll be clear what this means. Okay, and I want to be embedded, that one, and that one. Okay, so here's our first example. Please pause the video, answer this question, and then come back to the video. All right, so it says, I'm assuming you've done that. Given the two functions f of x and g of x as shown, what is the composite of f and g at 2? So what this is saying, it's saying evaluate function g at 2, that function at 2, whatever the result, embed it inside f and evaluate f. So let's do that. Function g at 2, we're evaluating the inside, is that 4 minus 2 squared. 4 minus 4 equals 0. So now this 0 is g of 2 is equal to 0. So we need to replace this 0 inside f, as this notation is saying. So the function f at 0 would be 7 times 0 minus 4. It will be 0 minus 4 or minus 4. They're not well, this is just a final number. So that's all they're asking. Now here, they're asking us to take the composition of G and F in 2 or at 2. At 2. So what does this mean? That means evaluate function f at 2, whatever the result, embed it inside G and calculate the final answer. So let's do that. So I'm going to evaluate f at 2. Function f at 2 is 7 times 2 minus 4. So that is 14 minus 4 equals 10. Right? Well, let me, not yet. So that's f at 2. So that 10 gets replaced inside G. Right? So 10 goes inside G right there. So G at 10 equals 4 minus 10 squared equals 4 minus 100 or minus 96. That is the final answer. And before I post these lecture notes on Canvas, I will make sure that I white out that, because that's just the function f at 2. It's not the final answer. This is the final answer. Okay, so the function f at 2 is equal to 10. We found that out. Okay, function f at 2 is equal to 10, which is there. All right, once again, please pause the video, answer this question on your own scratch paper, and then come back to the video. So, given two functions f and g, calculate, now this is the other notation, right? So calculate composition of f and g at negative 2, and g, composition of g and f at negative 2. So we're reversing those two functions. The order of the composition function, we're reversing that order. Okay, so what does this mean in terms of the other notation? It means the second function goes inside f. So is this one. f goes inside g in this case. Okay, so that means we have to do this. We have to calculate this composite function. Evaluate g at -2, whatever the result, put inside f and evaluate the function f. So let's first evaluate g at -2. G at -2 would be 2 minus -2 squared. 2 minus -2 squared is positive 4. This minus distributes itself to that. 2 minus 4 is equal to -2. So that's the function g at -2. Now we need to put this result in f, right? We just calculated this piece. So now function f at -2 will be 5 times -2. That's -10, -4, -14. And that is the final result here. Okay. I hope this agrees with what you have in your own solution. This one. So this is saying replace f in g and then calculate the composition function. So in other words, calculate g, composition of g and f at -2. That's what they're asking. Right? The second function goes inside the first one, just like what I've shown. Okay? So we need to evaluate function at -2 first. Function f at -2 would be 5 times -2 minus 4, right? Minus 4. So we have -10 minus 4. That's minus 4. Minus 4. Minus 14. Now, this is, minus 14 is function f at -2, that piece. So now we need to replace -14 for x in g. So g at -14 is equal to 2 minus -14 squared, right? I just replaced x in g with -14. So 2 minus -14 squared, it's going to be some positive number, right? Because this power is even, and it will make this negative positive. So let's see. 14 squared, 196, right? Or, if you prefer, I'm going to open parentheses, put in -14 and square that, and we get positive 196. Okay? So 2 minus 196, or minus 194. Here's the final result. Oops. Okay. All right. So this time we have these two functions, f and g, and they want us to, this one is interesting because they want us to take the composition of a function with itself, composition of f with itself, composition of g with itself at these two numbers, right? -1 and 2. Okay, so please pause the video, write down your own solution, and then come back to the video. These are just reminders. Okay, so composition of f with itself, that means put f back in itself and evaluate whatever the result is at -1. This one says put g back into itself and evaluate the resultant function at 2. So let's do that. So f going inside itself, that means that x must be replaced with 5x minus 2. So this, I mean, the equivalent notation would be this. Like that. That's the question mark. Okay? So evaluate. Because we have a number, sometimes they don't give us, or they don't want us to calculate the composite function at a number, but they want us to calculate the composite function at a variable. Okay? Those make the situation a little more complicated, but this actually, the fact that we're evaluating the composite function at a number makes the situation simpler. So because we can simply calculate f at -1 and replace whatever the result back into f again. But in the next example, this is number 3. In number 4, we'll get to when we're asked to calculate the composite function at a variable. Okay, we'll get to that. Okay, so let's first find function f at -1 and then put the result back into f again. So f at -1 would be 5 times -1 minus 2, right? I just replaced x with -1. So 5 times -1 is minus 5. Minus 2, minus 7. Is this the final answer? No. This is just function f at -1, right? We calculated that. Now we have to put this -7 back into f to calculate the composite function of f with itself. So again, function f at -7 this time is equal to 5 times -7 minus 2. So we have -35 minus 2 minus 37. That is the final answer here in this case. Okay. I hope this agrees with what you have in your own solution. So this is saying take the composite function of g with itself. So we need to put, well, it's asking us to do this, composition of g with g at 2. That's what it's asking. So let's find function g at 2, and then whatever the result, we're going to put back in g and evaluate g once again with that new number. Okay, so first let's calculate g at 2. G at 2 would be this function at 2. 3 minus 2 squared. 3 minus 4, right? -1. So now we put this -1 back into g again. So g at -1 is equal to 3 minus -1 squared. So we have 3 minus +1. 2. Okay, there's that. Okay, so given the two functions, f and g, compare this with what we just did, right? So every example we've done so far, the composition function was evaluated at a number, right? At a number. This time, no, though. It says find the composition function at x, and then, so that means we're going to get a new function, right? A new function which is a composite of these two f functions, f and g. And because of that, we need to find the domain of the composite function. Okay? And we've talked about that, right? So now you'll see how that works in practice. So this is saying put g inside of f, right? That's what they want us to calculate. The second function goes inside the first one. Okay, just like what I've shown. Okay, so if g is going inside f, where can it go? It can't go into 1. 1 is a constant value. The only place that g can go is in x. So all of g, which is 2x plus 8, is going to replace x. So that is equal to 1 over 2x plus 8. That's the composite function. There. We've answered that. But now, they want us to find the domain of this. Okay. Let's focus on this, and then we'll talk about those two. Because not the domain of both of these matters. Domain of one of these matters when we're trying to find the domain of the composite function. Not both. This is different than the combined functions. Okay, so the domain of this must exclude whatever x value that would make the denominator equal to 0. Because in that case, we're going to have an undefined function, right? So let's find what that x value is that we need to exclude from the domain. So 2x plus 8 equals 0. Whenever that happens, we're in trouble, right? So we need to make sure that never happens. So find the x value. 2x equals minus 8, right? 8 is positive on this side. When I move it to the other side, is negative 8. Why am I doing this? Because we're solving for x, and solving means isolating the variable. So I need to get rid of this 8, and I need to get rid of this 2. So the first step, I move 8 to the other side. So x is now a little more isolated than before, right? It just has 2 next to it now. We need to isolate x more in order to solve for it, right? So divide both sides by 2 to get rid of that 2. So x equals minus 4, right? So that number will make this denominator 0, which is trouble. So we need to exclude this number from the domain. Okay? We know that. So exclude from the domain. Are we done? No, not yet. Because how did this composition function came about or come about? It came about by replacing g inside f, right? So that the domain of this composite function must satisfy the domain of this g, which was replaced inside f. Not f, but the domain of g. So let's look at g. The domain of g is everything. Negative infinity to infinity, right? There's no restriction on x here. So we're okay. We're okay. The only number that we need to exclude would be negative 4. There is no number that we need to exclude because of function g. Because that was the function that was replaced inside f. We're not going to worry about that. That's okay. The function that was replaced in the other function was g. That's the domain we need to be concerned about. Okay? So because g is okay, then the only number we need to exclude from the domain is negative 4. So the domain of this composite function is negative infinity to negative 4 union negative 4 comma infinity, right? And the parenthesis next to negative 4 guarantees that negative 4 is not going to be part of the solution or the domain, okay? And if you're wondering how we got the two pieces, it's really easy if you draw a diagram for yourself. We don't have to draw it, but sometimes it makes understanding things easy, right? That's the real number line. Negative 4 would be somewhere here. Let me put a hollow circle there. We've determined that negative 4 should not be part of the domain. So what should be part of the domain? This piece, which is negative infinity to negative 4, excluding negative 4 right there, union negative 4 to infinity, which is that piece. Okay? All right, so this one wants us to calculate the composite function in this order. Put f inside g. Okay, like that. In other words, they want us to calculate this composite function. This is the equivalent notation to that. Okay, so we need to put f inside g. So wherever you see x in G, we need to replace it with f. Right? F goes inside G. Where can it go? It can go into 8. It can go into 2. The only place it can go is replace x. Because x is a variable. It can take any value. In this case, it should take the value 1 over x. So we have G composition of f is 2 times 1 over x. Notice what happened. The x in G was replaced by f, all of f, plus 8. Let's simplify this a little bit. 2 times 1 over x is 2 over x plus 8. Okay, so looking at the composition function, right away you can tell that x cannot be 0, right? So the domain of this composite function is everything except x, except 0, because 0 would make the denominator on this function undefined. Okay, so now we're not done yet, because we have to look back at the domain of the function that was replaced in G, which is f, right? If we look at f, the domain of 1 over x also excludes 0 from the domain, right? So both functions, the function f, which was replaced inside G, and the composition function agree that 0 should be excluded from the domain. So x not equal to 0, both in the for the composite function and the function f, which was replaced inside G. And those are when we determine the domain of the composite function, those are the only two domains that must agree. So we write down domain is negative infinity to 0, parenthesis or bracket. We're excluding 0, so parenthesis, union, parenthesis again, 0, comma, infinity. And that's because if we draw a graph here, we've just decided that x equals 0 cannot be part of the domain, right? So I'm going to put a hollow circle. Then what can be part of the domain? This piece, negative infinity to 0, excluding 0, there's that. Union 0 to infinity, that piece, which is that. Okay? So here, it says given the two functions 7f and g as described here, find G composition of f and its domain. So here f comes second, right? So f should be replaced inside G. Please pause the video if you haven't done this already. Answer this question and part B of the same question. It has a part B, which right there, yeah, you can see it right there. And then come back to the video and see my solution. All right, so this is saying composition of G and F. That's what they're asking us to find. F goes inside G, like I've shown. So where can F go? F cannot go inside 7. 7 is just a constant. It's fixed. But X is variable. It can change. It can become anything it wants, anything we tell it to be. So in this case, we're telling X to be 7 over X in each case. So let's do that. That is equal to, instead of X, replace it with 7 over X. In the denominator, instead of X, replace it with F. Plus 7. Okay, so this is, we quickly notice that we have created a complex fraction, right? We need to take the common denominator here, simplify that, and then simplify the whole complex fraction. All right, so let's do that. I'm going to take the common denominator for these two first. So I'm going to keep that the same, 7 over x. Now the common denominator here, the denominator of 7, what is it? It's 1, right? So the common denominator between these two would be x, right? It would be x. So let me do that calculation here on the side. So 7 over x plus 7 over 1, right? So if the common denominator is x, the first fraction is okay because it's got a denominator that is equal to the common denominator. But is this okay? No. How can we make this okay? We multiply the denominator by x to get it to become the common denominator. But the rule is we can't do this and not do the same thing to the numerator. So we got to multiply the numerator by x as well. Okay, now we're okay. So what do we have? 7 over x. So now that the denominators are common, we can add the numerators. So 7 plus 7 times x is 7x. Okay? In other words, we can factor this out. Let's factor this to, we can factor 7 out. We can say 7 times 1 plus x divided by x. Okay? Factoring is the opposite of the distributive property. So if you redistribute the 7 into this parentheses, you will get 7 times 1, 7. Plus 7 times x, 7x. So we get that the previous expression back. So our factorization is okay. Okay? So all of that was to combine these two fractions, these two. Now that we have that, I'm going to put this in the denominator. So this is going to go here. 7 times 1 plus x divided by x. Okay, like that. All right, so in the previous videos, I mentioned the easiest way to simplify a complex fraction. Do you remember how I talked about that? Let's do that. So to simplify this complex fraction, we look at the terms that are farthest away from each other. 7 and x are the farthest away, right? Multiply them and put them in the numerator. 7 times x in the numerator. Then take a look at the terms that are nearest each other, x and 7 times 1 plus x. Multiply them and put the result in the denominator. There. Right? 7 times 1 plus x times x. That's what we have. So now, is there anything we can do to simplify this? Absolutely, right? X and x cancel because everything is being multiplied, right? Remember, if there was addition or subtraction between 7 and x, we could not do that. We can simplify x and x because everything is being multiplied and divided here. And then also 7 and 7 cancel out. We end up with 1 over 1 plus x. So this is the composition function of g and f with f inside g. Okay? So now they're asking us to find the domain. So the domain of this, the final domain, should satisfy not only that, which means we can't have -1 here, right? It should satisfy this. And also the domain of the function that was replaced in the other function. Which function is that? It's the function f. So the domain, the final domain, should satisfy this requirement and that requirement for f. Okay? Because f was the one that was replaced. So for the domain, these are the two functions we're interested in, that one and that one. So domain would be exclude anything that would make this denominator 0. So 1 plus x equals 0, x equals negative 1, exclude from domain. Also, f of x, let me move this up a little bit. So f of x equals 7 over x. Therefore, x equals 0, exclude from domain. So the final domain then is, we got to exclude these two numbers. Negative infinity to negative 1, parenthesis, because we're excluding negative 1, union negative 1 to 0, union 0 to infinity. So that is everything except negative 1 and 0. Right? And if you have any questions at all about this, let me draw a quick graph here. Negative 1. So we want to exclude 0 and negative 1. So what can we include? We can include this piece, and that piece, which is these three pieces that you see. Negative infinity to negative 1 is that piece. Negative 1 to 0 is this piece. 0 to infinity is this piece. Okay? Do you see how this works? If not, let me know, please. Ask your questions. Okay, so part B, let me write down the functions here because they're off the screen. Function f is 7 over x, and function g of x is x over x plus 7. So now it says take the composition of g with itself. G with itself, right? That's what that is saying. G embedded or replaced in itself. Okay, so if I'm going to put g in g, that means everywhere I see g, x, I need to replace it with the entire g. So that is asking us to do this. G inside G, as you can see here. So that is equal to, I moved down a little bit because I won't have enough space there if I start here. So all of G should go replace G in the numerator. So x divided by x plus 7 divided by. Notice x is gone. What has replaced it is all of G. That's what it means to replace G in G. I got to do the same thing in the denominator. So this x is going to go, it's going to go away, and it's going to get replaced by all of G. So x over x plus 7, and then of course plus 7. So x in the numerator and the denominator is gone. Instead, it was replaced by x over x plus 7 in the numerator and the denominator. So where you see x over x plus 7 and x over x plus 7 used to be x in G. Now it's entire G for each x. Of course, this is going to lead to a complex number, right? So let's see what that is. So we need to combine these two first. So x over x plus 7. We need to take the common denominator, right? Let me take the common denominator in this corner if you don't mind. So this for common denominator for these two. So we have x over x plus 7 plus 7. The denominator of 7 is 1, right? So what is the common denominator between this x plus 7 and 1? The common denominator is x plus 7. Oops, I didn't want to put that so close, so let me put that like that. It's equal to x plus 7. That's the common denominator. This fraction is happy because it's got a denominator that is equal to the common denominator. But this one is not, right? So it wants the denominator 1 to become x plus 7. How are we going to be able to do that? Well, we're going to multiply the denominator by x plus 7. Sorry, sorry for cramming this stuff. X plus 7, and also the numerator multiplied by x plus 7. So what are we going to get? We're going to get x is x plus 7 times x plus 7. 7 times x plus 7. Okay. Now, let's combine the terms in the numerator. We have, I'm going to distribute the 7. So we have x plus 7 times x is 7x. 7 times 7 is 49. Divided by x plus 7, right? Now let's combine 7x and x. What do we get? We get 8x plus 49 divided by x plus 7. So I'm going to put this in the denominator of that. We did all of this to combine these two fractions here. Now that we're done doing that, let's put it there. So we have this piece, that piece goes there. So we have 8x plus 49 divided by x plus 7. Okay? Now that we have one fraction in the numerator and one whole fraction in the denominator, we can do what I was talking about earlier, which is the easiest way to simplify a complex fraction. Take a look at the terms that are farthest away from each other, x and x plus 7. Multiply them and put them in the numerator, like that. The farthest terms that are farthest away from each other. Divide that by the product of the terms that are nearest each other. So x plus 7 times 8x plus 49 in the denominator. So x plus 7 and x plus 7 cancel out because they're being multiplied by x and multiplied by 8x plus 49. So what do we end up with? We end up with x divided by 8x plus 49. That's the composite function. Now the domain. So to find the domain, we are interested in a domain that satisfies this composite function as well as the function that went inside the other function to give us this function, which is g. So the domain, the final domain, has to satisfy these two functions, not f. We don't bother with f, right? Just these two. So the domain, let me Here we have 8x. We have to make sure that this denominator is never 0. So 8x plus 49 equals to 0. Then x equals negative 49 over 8. Right? That should be excluded from the domain of this composite function, for sure. So let me write here, exclude from domain. Also, the original function that went inside g was g itself, right? So in that function, we could not have x be equal to negative 7. We could not have that, because if it was, it would make g undefined. So also, this is the second piece, g of x equals x over x plus 7. X plus 7 equals 0. Then x equals negative 7. Once again, exclude from domain. So the domain of this composite function must agree with the domain of itself and also the domain of the function that went inside the other function, which is g. So the domain of this composite function is negative infinity. We need to exclude these two numbers. Now, for negative 49 over 8 is negative 6 something, right? See? So it's a slightly larger negative number than negative 7. So negative 49 divided by 8, see, negative 6.125. So this number is a little bit larger than negative 7. So this would be negative infinity to negative 7, union negative 7 to negative 49 over 8, union negative 49 over 8 to positive infinity. That's the domain of that composite function. Okay. So the yellows show you which functions need to have their domains agree with each other. Okay? All right. On this page, they say find f of x and g of x such that h of x is equal to composition of f and g in x. Answers may vary. Yeah. So that means you could have answers that are different than mine, but they are accurate. So we don't have to end up with the same answer. That's what it's saying. But they have to make sense. Okay. So what this is saying, it's saying that what you see here given to you is the composite function, and they want us to find the parent functions f and g. Okay, so notice this notation means that this h of x was formed as g went inside f. Right? So we have f, that. That's what we have. H of x is that. G went inside f. And we have that. Okay? So again, please complete this page. You have A through E. You have 5 examples here, exercises on this page. Please pause the video. It should not take you more than 6-7 minutes. This is a really easy exercise. Should not take you 6-7 minutes. And then come back to the video and see. And keep in mind that for this exercise, our answers may vary, even though we all can have an accurate answer, but our answers may differ from each other. So this is saying if G went inside F and it gave me this, then F must have been x to the fifth, and G must have been 4, or I didn't even need the parentheses, so 4 plus 3x. So there you have it, F and G. Now if you put G inside F, you're going to get that, 4 plus 3x to the fifth power. Okay, so that's one correct response. You might have one that is different than this, and it could be accurate. This one, but I would go with the easiest one. You don't have to make the functions very complicated. Pick the easiest parent functions. For example, that one, G went inside F to give us this. So I can quickly write f of x, like I say, make it as easy as possible. The third root of x, that's f, and then g of x is x squared minus 8. So now if you like that and like that. So now if you put g inside this function f, you're going to get that, h of x. Okay? So pick the easiest parent functions possible. Look at that. That could be really easy, right? So function f could be something like this, 1 over x. Right? Just 1 over x. Function g then could be square root of 3x plus 7. Like that. All right. So here, again, I hope these answers agree with what you have as your own answers. Okay. So this is the opposite of what we've been doing. We have been given, in this case, we have been given the composite function, and we're asked to create the parent functions or find suitable parent functions. All we're looking for are suitable parent functions. So that one, I could do f of x equals absolute value of x, right? That could be f. And g, which was the function that went into this, could then be g of x equals 9x squared minus 4, and we're done. Right? We're done with that as well. You put this g inside f, you're going to get that. That one. It looks complicated, but it's really not. We can make this very easy. So f of x, we can say make f of x equal to square root of x. We can make it as easy as that. Right? Then for g of x, we can write 1 plus square root of 1 plus x. So now you replace g inside f, you're going to get that, right? Square root over all of this. Like that. All right, so we've come to the conclusion of another section. The key to learning all of this is that you solve the problems ahead of me, then check with the video, and that way I'm sure you will be very happy with your progress in this course. Okay, so For now, have a nice day, and I'll see you all again next time.